Good morning, everybody. I hope you had a pleasant evening, and I'm praying for you that you're going to have a great day today. And so we're about ready to go back over some things. I know that on the very last slide yesterday, we may have gone a little bit fast, so I want to give you an opportunity to make sure you write down all those things I said towards the end of yesterday's lecture. So make sure that you write down that a mixture is two or more substances that can be separated by physical means. And if you recall, a substance is something that's made of only one ingredient, so if you mix a couple of them together, a couple different ones, then you get what we call a mixture that can be separated physically. Okay, we also said, for example, you could have a salad. So if you didn't write down the salad, you can write that down. So you could pick out all the different parts. Okay, some of you probably already have this, but just in case, sand and iron. And I said yesterday, if you mixed up sand and iron together, you could take a magnet and sweep it right through. And after sweeping it right through, the iron parts will stick to the magnet and it'll leave the sand right behind. So you could write down sand and iron. You could take a magnet and the iron parts would cling to the magnet, leaving the sand behind. Okay, so my plan is that this whole salt water idea, if things go well, we should have set up an experiment on Wednesday to demonstrate the saltwater separation. But if we didn't, then on Monday when we come back, we're going to be doing a mini lab where we're going to actually separate salt and sand and water. I hope that those are already going. If they're not, as I said, we will get to do that very early next week. So salt water can be separated. Okay, sometimes when you perspire, you have some salt mixed in with your perspiration, and that can leave salt stains on your clothes. Well, that's because the water actually evaporates and the salt is just left behind. Okay, and we should be able to see very well that process through the experiment that we're going to do or is in process right now. So there's not any chemical process happening. No chemical process needed. All you have to do is set it out on your table. And you set it out on your table, the water evaporates, it changes phase. The water's still there, it's water vapor. But once the water is gone, the salt's left behind. So if the salt and water are mixed, and it is left to sit out, the water will evaporate, leaving behind just the salt. And I can even imagine right now there are some of you who want to make a comment. I would love to be able to hear your comments, and I will when I come back. So if you've got something really important to say, make sure you jot it down so that you can remember to bring it up next time we have class. Okay, these are physical processes. They do not need a chemical reaction to happen. So physical processes mean you're not having a compound break down and turn into something new. You still have the same ingredients that were mixed together in the first place after they've been separated out. So these, write it down, these are all physical processes and do not need a chemical reaction to happen. All right. So it's time to move on a bit. There are different types of mixtures, and we're going to talk about them. I have organized them into a chart, so that you can see them, but then we're going to break down each different individual type. Okay, so let's bring this up. We have mixtures. There are two types of mixtures. There's heterogeneous and there's homogeneous. Hetero means different. Homo means same. Heterogeneous, different throughout. Homogeneous or homogeneous, depending on how you pronounce it, is the same throughout. So heterogeneous mixtures are chunkier, and homogeneous mixtures appear to be the same throughout. Okay, these have more of an appearance of being different throughout, and these are the same throughout. Okay, so that's what those prefixes mean, and then they get attached to these words that apply to mixtures. Heterogeneous mixtures, we have a whole variety of them, so I just put other here. This isn't really a technical heading, but anything that doesn't belong under the suspension category, which I will very carefully define shortly, is just another random heterogeneous mixture. Homogeneous or homogeneous falls under two categories. We have solutions and we have colloids. So what I'm going to do is I'm going to break down all of these very carefully and give you some definitions. Now, when I'm doing it, I'm keeping the same basic chart so that you can constantly be reinforced what you see, but in your notes you're probably just going to write down what these different definitions are. But remember, they do fall under this whole heading, these whole categories. Now, if you wanted to, you could get yourself a big piece of paper and write the definitions right underneath each one, so that it would be all there in one big chart. But I like this organization of the information so that you can keep track of all of it. So let's start with heterogeneous mixtures. More than just saying chunky and different throughout. A heterogeneous mixture is a mixture in which different materials can be easily recognized. A heterogeneous mixture is a mixture in which different materials can be easily recognized and the proportions are different throughout. All right, so one place that you take a look at a heterogeneous mixture may be different than another place, even if it's in the same container. Okay? For example, pizza. Pizza is a heterogeneous mixture. Okay? All those different things that went into your pizza are all mixed together. You've got the sauce, the cheese, and whatever toppings it is that you like. But even if you order a pepperoni pizza, it's not going to be exactly the same throughout. The pepperoni will be placed a little bit differently, even if you're super careful. You can't get it in the exact same proportions all the way throughout. Okay? So it is a heterogeneous mixture. The pieces and parts of a pizza are very easily recognized. You don't have to do much thinking to be able to identify what's the sauce and what's the cheese, and even the oregano kind of sticks out a little bit. Salad, once again, that's a pretty simple one to identify. Different places in your salad bowl will have different proportions, and you'll be able to easily recognize the different pieces and parts inside your salad. Another example is concrete. You may not think about concrete as being a mixture, but it is even when it's dried out. Concrete, if you've ever seen it mixed, and if you haven't, I'm just going to explain it to you. They put some rocks in. They put a material called cement in there. They add some water, and they stir it all up. And if you've ever had the opportunity to stir up cement, you would know that there's various different chunks, different proportions of rocks at different places. The water will evaporate and leave behind the rocks and cement, but there will be a certain amount of water in concrete for many, many years. I heard that I had heard it said that 100 years later there's still a little bit of water left, and it's not completely set for 100 years. Now it will be very set. Okay, but it won't actually have all the water out of it for all that time. So concrete is a mixture. Parts easily recognized? Well, from the top, when it's all smoothed out, it's kind of hard to see all of the parts. But if you stirred it up a little bit, you could begin to see the parts. When I say easily recognized, it doesn't necessarily mean that the particles are giant. You might even need a microscope to recognize the parts, but the parts are definitely there, and they're definitely something that you could tell. One that's a little bit harder to see the different parts and fibers is a lot of us wear clothes that are mixtures of different types of threads, different types of cloths. Cotton and polyester frequently are mixed together on clothing. You might need a microscope to pull it in so that you could see which fiber was which and identify them. But cotton and polyester it's a blend, and it's what we would consider a mixture. It's heterogeneous. It's not the same throughout, even in that clothing. If you took one little square and you took another little square and you compared them, you'd find out that the one square was very different than the other square as far as their proportions. Okay, so heterogeneous, different throughout. I want to look at one of the subcategories of heterogeneous mixture. Okay. Hopefully you've had a chance to write down the pizza and the salad and the concrete, which is made of rocks plus cement plus water, and also that cotton polyester blend clothing fits into that category as well. Okay, moving right along. Under the heterogeneous category, we have something called a suspension. Okay, and a suspension doesn't mean somebody's out of school. A suspension is a certain type of mixture. Okay, it is when the particles are pretty well mixed, but they are going to settle out. So in other words, if you stuck a jar of whatever this mixture was out, eventually what would happen is particles would begin to go to the bottom, and some of the particles would be at the top. Those heavier particles would settle or go down into the bottom. A good example of that would be if we went out to the pond and we took a nice big bucket from the pond. It might be all stirred up and it might just look like muddy water for a while, but if you set that thing out for a while, the mud would begin to settle to the bottom. And so you would have water on the top, and maybe there would be some little microorganisms that would be swimming around in there somewhere, and there might be some kind of algae in there, but it would start to go to its different levels. The dirt would settle to the bottom. It's pretty well mixed. The particles were suspended in it, but they fell out so that you have that stuff in the bottom. Okay, river deltas, that's basically just a fancy name for the same thing in a river. Okay, so make sure you write down that a suspension, in a suspension, that's a heterogeneous mixture. The particles can become fairly well mixed, but will settle out eventually. Or quickly. Sometimes they settle out really, really, really fast. For example, if you mix up sand and water and you shake it up, the sand will fall down really, really fast. In our example, muddy pond water or river deltas. Okay. And if you're kind of thinking, I wonder if such and such is a suspension or not, you can ask me when you see me on Monday. Okay? I want to take a look at this other category, even though it's not technically really its own category. That's any other heterogeneous mixture, such as salt and pepper. If you mix salt and pepper together, you're going to have a heterogeneous mixture. It's not really considered a suspension. The salt and pepper may not separate out, but you'll have different proportions throughout. If you have an ice cream sundae, it's not really going to settle, although sometimes the syrup will go to the bottom, or the hot fudge or anything good like that will go to the bottom. But it's not really what we call a suspension. It's something different. Tacos. I think I'm stuck on food here all of a sudden. These things, they're mixed up, but they're not going to actually just settle out. They're chunky, if you want to put it that way. Heterogeneous, they're different throughout the different pieces. It's pretty obvious that there's different proportions, but there are more than just suspensions in the heterogeneous category. So what we need to do is take a look at the homogeneous category. Some of you might say, wow, Sister Dottie, that sounds like homogenized milk. And yeah, it does. Because homogenized milk can be shaken up or made so that it is very, very well mixed. It doesn't happen to be under the solution category. We'll figure out in a minute what category that's under. It's the other one, it's the colloids. But solutions are the best mixed of the mixtures. When you have one substance is actually dissolved in another substance. A solution is when one substance, oh, there's a typo there, isn't there? One substance is actually dissolved in another substance. So when you mix sugar into your hot tea, the sugar will dissolve into the tea and you have a solution. When you have salt and you mix it into water, the salt will dissolve into the water and you have a solution. Now, your book doesn't mention it, but I just can't help but mention it because it's good to have heard the words. The solvent dissolves the solute in a solution. So in other words, the solvent would be the water and the solute would be the salt. So the salt would dissolve into the water. The solvent dissolves the solute. Okay. The solvent dissolves the solute. Most people are usually at some point in their life have heard the word solvent. It's that solute word that you usually haven't heard, but it's right in the word solution. So it's part of it. Okay, the particles in a solvent, in a solution, are so small that they won't settle out. They're considered the best mixed of the mixtures. So when you have the salt water and the salt has been mixed in and it is dissolved in the water, it's considered, it's a solution. It's not gonna, the salt's not gonna just fall down to the bottom. It's gonna stay mixed in. It is the best mixed. It's not gonna settle out. Now, throughout the salt water, you'd find different proportions. So they are still a mixture. It can still be separated by physical means. But the solution is as close as you get to having fixed proportions. Okay, so let's make sure we write down that the particles are so small they won't settle out. And that this is the best mixed mixture. So we should have some examples. I mentioned a couple. Salt water. Salt water is an example of a solution. It's salt dissolved in water. So that they're together, they're acting like one thing even though they're not. And hot tea, you take the tea bag, you put it in the water, and the tea leaves will, that tea will work its way through the water and it's going to become a solution. Now sometimes when you have tea, some of the tea leaves will settle out. So that's not, but the actual coloring, that brown coloring from the tea leaves will stay in and it will be a solution with the water. So you do have solutions there. Okay. That leaves us with colloids. Now colloids are one of those things that you've all encountered colloids, but you didn't know they were colloids. Okay, colloids are also homogeneous mixtures, well mixed. In other words, they're pretty much the same throughout, just like our prefix means, the same throughout. So in a colloid, the particles of one substance are permanently suspended in another. They are not quite as well mixed as a solution, but the particles of one substance are permanently suspended in another. Now when I say permanently, I mean that they're there until somebody does something physical to separate them. In a solution also, they are together until something has happened to separate them. Okay, but they're not going to just fall apart like in a suspension. The things just fall apart because of gravity. They won't settle out. A colloid will not settle out. Okay, so examples. And I'm a little bit sad the book that we used to have would actually make categories for these, but I'm not going to add that much to this book for you. But there's actually subcategories under colloids, various different things that we can take a look at, but I do want to look at some examples of colloids. One substance is suspended in another. They sometimes don't act just like a solid or a liquid or a gas because they're mixtures. They're a couple things put together. One example is fog. Okay, you have fog and you drive through it. The fog is actually little tiny water droplets that are suspended in the air. Now, eventually the water droplets will evaporate and become water vapor. Okay, but they're not suspended in that air pocket, so they're not being carried along as one package called fog. So fog is a colloid. Another one is paint. Okay, paint in the can. Paint has little pieces of solid pigment that are suspended in a liquid. Okay, it's called a sol. If anybody's ever looking for a word that you can use in Jeopardy or whatever, it's called a sol. The solid is suspended in the liquid. So you paint it, and what happens is the water, the liquid evaporates, and you're left with the solid pigment on the walls. Smoke. Smoke has solid pieces that are suspended in gas. So smoke actually has solid pieces. So when you breathe in that smoke, the solid pieces are trying to go into your lungs. Your lungs are not made to have solid pieces in them. Okay, I don't know if you have ever been camping and you breathe in the smoke around the campfire, and later you go home and you blow your nose and you find that there's all this brown junk when you blew your nose. Those are the solid pieces that were being carried along in the smoke, and when you breathed it in, your nose is designed to try and capture some of that. You've got mucus in there that's going to protect you from things that are being carried along by the air. In this case, it's carried along by the smoke. However, you're not usually just breathing through your nose, you're breathing through your mouth. Or cigarette smoke will get those things, those solids will be carried along into your lungs, and your lungs are not designed for solids. So it's hard on your lungs, first of all, but then those little particles in there, some of them are carcinogenic and will cause cancer. So smoke, solid, is suspended in a gas. Gelatin dessert. I put up gelatin dessert to avoid copyright infringements. You probably know it as the trademarked name Jell-O. So Jell-O has is a special type of substance. It's actually a liquid suspended in a solid. So that's why Jell-O doesn't really act like a liquid. It doesn't really act like a solid. It's its own thing. It's a colloid. It's special. Okay. I didn't put it in here, but whipped cream also follows that. Clouds are just fog in the sky, but clouds also fit under this colloid section. Okay, so that actually covers all of our categories. We do need to do a little summary and have a little bit more information, but mixtures broken down into heterogeneous and homogeneous, suspensions, and the rest of the heterogeneous mixtures, the solutions and the colloids under homogeneous, and what we do need to do is take a look There are two types of substance. There are two types of mixtures that actually, when you shine a flashlight through them or light tries to pass through, because there are particles suspended in other particles, we say that they scatter light. Some mixtures will scatter the light. Okay, if you shine a light, and there's a whole bunch of dust, you can actually see the dust particles, and it scatters the light. So at that point, there's some kind of mixture of air with dust. Okay, if you try to shine a flashlight through pond water, okay, it scatters the light. It makes it cloudy appearances, clouds themselves. Okay, you try and shine a light through it, or if you've driven through fog, you try and shine a light through it, and the light scatters and it gets this cloudy effect. There's a special name for that. It's called the Tyndall Effect. Okay, and you're responsible for that as vocabulary. The Tyndall Effect is what causes that cloudy appearance. It's actually, remember, the light waves are extremely thin, and when they hit these different particles, they will bounce off in strange directions, and so it makes it so the light is not traveling in the path that it normally would, and it gives it that cloudy effect. Make sure, let's write this down. Some mixtures will, quote unquote, scatter light so that when a light shines through them, it looks cloudy, and this is called the Tyndall Effect. Okay. Now there's two types of mixtures that we've already talked about that experience the Tyndall Effect, and that is colloids and suspensions. Colloids and suspensions will both appear cloudy, and so they are experiencing the Tyndall Effect. Suspensions, pond water, you shine the light through and it gets all cloudy looking. Colloids, if you shine a light through any of those things that we mentioned, paint would be hard because it's got all that pigment in it. It's opaque, so it doesn't really have the Tyndall Effect, but the clouds and the smoke and the fog and even Jello to some extent has a cloudy effect. So it's that Tyndall Effect that's making that happen. Colloids and suspensions appear cloudy, so are experiencing the Tyndall Effect. Alright, so I have broken this down into a chart for you so that you can get some of the important qualities of the different types of mixtures as a summary, so that when you're studying it'll be a little bit easier for you to put these ideas and things together. So we're going to break it down into solutions, colloids, and suspensions. Leave yourself plenty of room in your notebook so that you have enough room to include the whole chart. Okay, so you're going to have 4 columns. The left-hand column is going to be need to be large enough to have words, but then the headings on the next 3: solutions, colloids, and suspensions. Okay. Okay, first of all, the first thing is the particles will settle out. The particles will settle out. In a solution, they will not settle out. In a colloid, the particles will not settle out. But in a suspension, the particles are going to settle out. Some of the particles will end up going to the bottom. Okay, so that hopefully the visual will help you when you study. Make sure that, especially over the weekend, you're going over your notes, making sure that you understand everything. Can be separated with filter paper. Some things, when you pour them through, will allow them to be separated, and some things will not. Solutions cannot be separated with filter paper. If you pour salt water through a filter, you're going to have salt water coming out of the filter. The particles are too small to be caught with filter paper. A colloid. If you tried to pour the colloid through the filter paper, it's not going to hold anything back. Okay, you dissolve the Jello mix in the water and you pour it through the filter paper. It's not going to hold back just the gelatin mix. It's going to let all that stuff pass through. Okay, a cloud, you try to put a cloud, you sweep it with a piece of filter paper, it's not going to separate that thing. However, a suspension, if you have a suspension and you pour that through filter paper, then some of the particles will stay in and some will go out. The ones that are larger will stay in the filter and everything else will pass through. So yes, you can do some separation if you have a suspension. There is something to be said about the particle size. I'm not making you memorize the numbers that go with them. You'll find those in your book. But what I do want you to know is that in a solution, the particles are the smallest. And in a colloid, the particles are a little bigger. And suspensions have the biggest particles. So we can also divide this up by particle size. Smallest, mediumest, and medium, and largest. And finally, will they scatter light or not? Scattering light is a Tyndall effect. Solutions will not scatter light, but colloids will scatter light and suspensions will scatter light. So solutions do not experience the Tyndall effect. Colloids do experience the Tyndall effect, and suspensions do experience the Tyndall effect. Scattering light. Okay, so hopefully that chart will help you out. What I would like you to do with the remainder of your time is work on the Chapter 15, Section 1 self-check in your book. You may either turn in the book, the questions, or you may do the summary. Okay, either way, but I would like you to work quietly on that until the end of the period. I want you to go back over the book. Don't forget from yesterday, you're responsible for page 451 for writing down those examples of uses for the elements. So please make sure that you do that. And have a really blessed weekend.